Welcome to this explainer. Today we are diving into a seriously fascinating new arXiv paper that completely rethinks how AI agents conduct deep research. If you've been working with large language models and retrieval systems lately, well, you already know that building a truly autonomous research agent is incredibly challenging. It's tough. But this new framework is completely shaking up the conventional wisdom on how we actually get there. So let's kick things off with a pretty provocative question. Does a smarter AI always require a massive increase in parameters? Or is there, a more elegant solution out there? For the past few years, the entire industry has been totally obsessed with scaling laws. The underlying assumption has basically been to get better synthesis, deeper reasoning, and more accurate retrieval, you just need a bigger model. But this new research, it challenges that fundamental assumption head on.
Get this. An 8 billion parameter model is now outperforming static 32 billion parameter giants. It's proving that size really isn't everything anymore. That is a massive, massive difference in compute and memory requirements. We're talking about an agile, lightweight model punching way above its weight class. And the crazy part is, it's doing this not through brute force scaling, but through a totally reimagined architecture.
Here's our roadmap for today. We're going to cover the deep research ceiling, introduce the HOTE framework, break down the proposer, solver, and judge modules, see exactly why evolution beats static models, and wrap up with next steps for developers.
All right, part one, the deep research ceiling. Let's look at what is actively holding our current AI agent systems back right now. Currently, AI systems are basically split into two siloed paradigms, and both hit a really hard ceiling. On one hand, you've got current deep research setups. They're great at autonomous retrieval in unstructured environments, but their capabilities are totally frozen in place once they're trained. On the other hand, you have agent evolution. Now, this learns dynamically by interacting with its environment, but it's really only reliable when there's a deterministic, easily verifiable answer. And as we all know, open-ended research rarely has a simple, clean, right answer. The reality is, when the information landscape changes, these static RAG pipelines and fixed templates simply cannot adapt. Static models basically treat deep research like a simple retrieval and re-rank chore. They grab a few documents, shove them through a rigid template, and spit out a summary. But real research is messy, right? When a task scope unexpectedly shifts, these models expose their parametric bottlenecks and just begin to fail. Which brings us to part two. Enter the HOTE framework. This is the core of the new arXiv paper, and it represents a completely different angle of attack. HOTE, which stands for Hybrid Open-Ended Tri-Evolution, is a real game changer. It essentially collapses the boundary between research and evolution by treating research as a continuous, dynamic loop rather than a frozen set of rules. Instead of relying on a single monolithic model to do absolutely everything, it breaks the task down. It splits the workload into 3 distinct modules that actually evolve together through reinforcement learning. Now, what's super fascinating here is how this architecture allows the system to adapt its own search strategy, its synthesis depth, and even its evaluation thresholds on the fly during training. In a standard setup, you do some supervised fine-tuning and then freeze the model. HOTE doesn't do that. It runs the modules through a continuous reinforcement learning loop. If one module succeeds, it sends positive gradient updates to the others. It's a tightly coupled pipeline that literally learns how to research, rather than just regurgitating what it memorized during training. Let's move to part 3. The proposer, solver, and judge. We're going to do a quick autopsy on this next-gen AI model and meet the collaborative triad at its center. First step, the proposer. Think of the proposer as the lead scout of the team, constantly discovering the best questions to ask. It doesn't just randomly guess keywords. Over time, through this evolution loop, the proposer actively learns exactly which query formulations will actually return high-signal documents, instead of just pulling in irrelevant noise. Then you have the solver. This is the execution powerhouse. It does all the heavy lifting of reading and synthesizing the data that the proposer finds. But here is the brilliant part. Because it's constantly evolving, it specifically learns how to handle conflicting sources. Instead of just glitching out and hallucinating when 2 documents disagree, the solver actually learns to cross-reference and synthesize complex, multifaceted answers. And finally, the judge. The judge is the vital critic, evaluating the solver's work against web-scale knowledge to ensure absolute precision. It makes sure the system doesn't get lazy. It actively penalizes superficial summaries and only hands out high-reward signals for structured, traceable arguments. It makes evaluation an active, breathing part of the training loop, not just some post-hoc metric checked by developers after the fact. This whole setup brilliantly illustrates how the triad negotiates trade-offs. It uses what's called hybrid mode reinforcement learning. It takes discrete actions, like making the hard choice to search, read, or write, and blends them seamlessly with the smooth optimization of continuous policy gradients. It's basically like the AI intuitively knowing exactly when to keep digging down the rabbit hole and when to just stop and give you the precise answer. So, Part 4. Why evolution beats static. What actually happens if we break this dream team apart? Let's take a look at the paper's ablation studies. When the researchers tested this, they found that removing any single member of the triad completely breaks the machine. It proves all three modules are absolutely indispensable. If you take out the proposer, your queries lose all their diversity, and the solver gets stuck in these super narrow, useless retrieval paths. If you pull out the solver, well, the system obviously has zero execution capacity. And crucially, if you remove the judge, the entire feedback loop shatters. The system immediately starts reward hacking, basically finding cheap ways to score points without doing the actual research, and the output quality falls off a cliff. But when they work together, magic, because the reward signals are distributed across these specialized modules rather than all competing for a single policy head. This 8 billion parameter David absolutely crushes the 32 billion parameter Goliath, and it does it with less time overhead. This is a massive takeaway if you're building agents. It converges faster than monolithic RL training because the responsibilities are so cleanly divided. You get better performance, you beat state-of-the-art methods, and you burn way less compute time getting there. There's a quote from the paper that perfectly captures this massive paradigm shift. Parameter scaling becomes optional. Loop design and reward shaping take priority. You no longer have to blindly scale up to 32 billion parameters just to squeeze competitive research performance out of your AI. The focus is entirely shifting to how elegantly you can construct your reinforcement learning environment. Which brings us to our final section. Next steps for developers. How do you actually apply this to your own agent stack right now? Well, here is your practical playbook. Start by auditing your pipeline to move away from those static templates. If you're still using rigid prompt chains, you are operating in the pre-evolution regime. You need to map out where your proposer, solver, and judge roles currently live in your stack. And when you start building this, remember, step 3 is absolutely critical. Isolate your module updates. Train the proposer and solver separately first, then introduce the judge. The researchers found out the hard way that simultaneous, uncontrolled updates will degrade all three roles. To really get started, make sure you review the official GitHub repository. Pay super close attention to their environment configuration files and batch sizes because hybrid RL convergence is highly, highly sensitive to those factors. Treat HOTE as a blueprint for modular RL, not just some simple drop-in script. You really have to dig into how they set up web-scale knowledge ingestion in their environment wrappers before you try adapting it to your own custom data sources. So I'll leave you with this final thought. As the deep research ceiling officially shatters, are you ready to stop blindly scaling parameters and start evolving your loops? The era of treating an AI agent as a static, frozen-in-time entity is rapidly coming to an end. By embracing dynamic, collaborative evolution, we are unlocking a completely new frontier of truly intelligent, autonomous research. Thanks so much for joining us for this explainer, and we'll see you next time.